Welcome to classes by Inspire Physics. Today we are going to see the topic diffraction of light. Diffraction of light means it is a bending of light at sharp edges and corners of obstacles. So to understand the concept, first we will see a diagram. Suppose we have a screen is placed and we have a small slit made using a cardboard. The cardboard is having a small hole, so this acts as a slit. This is a slit, and we have a source. Slit has a width. Let us choose A. A is the width of the slit. We have a light rays coming like this. These light rays pass straight. Okay, these light rays pass straight. These are the light rays passing through the slit. So what we expect? We expect this region to be the bright region. Bright region means it is, if this is A, width is A, here we expect this width also should be A. And the remaining portion should be the dark portion. So this is bright portion. Bright portion. So corresponding to the slit, we get an image here. So this will be the lighted portion. We expect the lighted portion here. But in practice, what we observe is, among the light rays, a few light rays will bend at the edge of the obstacle. It will bend like this. So due to the bending, light enters in this region. So what happens? The width of the brighter region has further extended. This is the width of brighter region. And this width, if I choose a W for the width, this width will be more than what? The width of the slit A. Okay, so we can see the brighter portion having more area compared to this area. So a bigger patch of light we can see on the screen. See another example. We have a screen slit. We have an obstacle, a sharp obstacle like this. We have the screen placed here. Light rays passing straight. So these light rays will fall on the screen, and these portions will be lighted portion. So here we can see light. So lighted portion or bright portion. We can say bright. And here what we expect? Here we expect a shadow. Shadow of that obstacle. But in actual practice what we say is, so what happens to these light rays? These light rays are blocked by the obstacle. Now actually what we observe is, a few light rays from here, it will bend like this. Bend and enter this region. So the shadow region is slightly covering small area, but the lighted region is slightly extended like this. So this region we have a lighted portion, this portion we have a shadow. So this happens due to diffraction of light. So we can see that at the edges of the obstacle. So this is the slit, these are the edges. At the edges, what happens? The light rays undergo slight bending. In addition to traveling straight, a few light rays will bend at the obstacle. So these light rays are slightly bending. After bending, the light rays are occupying this portion. So the light reaches this region. So this portion will be lighted and this will be shadow portion. Here also, the width of the slit, when it falls on a screen, it is comparatively large. So the width is large compared to the size of the slit. Now this phenomenon is called a diffraction of light. Okay, this is called basically diffraction of light. Now we will see an experiment related to diffraction of light, that is called a single slit diffraction. So we will see a single slit diffraction. Okay, we are going to say single slit diffraction, and we need to derive expression for width of central maximum. Okay, so the same concept we are going to see here also. So we have a single slit. I have a cardboard. So in the cardboard I have made a slit. So I am drawing the slit in slightly bigger size. Actually the slit is very small in size. Maybe 0.2 millimeter or like that. This is a slit. And these are the parallel light rays. Parallel light rays are passing through the slit. Okay, parallel light rays. Now this is the incident wavefront. These are the incident wavefronts, plane wavefronts. Now this is another wavefront here. It is entering the slit. I mark 3 points on the wavefront. I mark this point A, this is B, and this is C. And now this is a screen. A vertical screen we place here. Now let us choose center of the screen. Let O be the center of the screen. Now according to Huygens principle, we know that each point on the wavefront act as source of secondary wavelets. They produce secondary wavelets. So wavelets from the points A, C, B, from all the points wavelets can reach at the point O. And we know that wavelets from A and B reaches O and there is no path difference. We observe that there is no path difference. So at the point O, wavelets from A and B reach. Not only from A and B, from every point the wavelets reach at the point O. And what is the path difference between the wavelets from A and B? They travel equal distance, so there is no path difference. Okay, so at O what we expect the brightest portion. So all the light waves constructively interfere at point O. We will have a bright point, so I choose B. Bright point will be there. At the point O, we expect a bright point. Now I just draw two horizontal lines from points A and B. This is a horizontal line. Okay, so this point will be the bright point. Now we need not have the line here. Now I can draw this point. So we know that the center point O will be the bright point. Why it is bright point? Because the wavelets from A and B travel equal distance to the point O. So that the point will be a bright point. Now what we expect on the screen, up to this portion the light is traveling straight. There are many wavelets traveling straight and produce a bright portion here. But due to diffraction effect, the bright portion is slightly elongated, as we have seen in the previous case. So we can expect up to this height. This may be the region from here to here we can expect. This may be the region where there will be bright portion. Not only in this region, more width we can expect for the bright portion on the screen. Now let us choose another point here. I choose a point P1. On either side I choose points. Here I choose point P1. Here I choose point P2. Let us choose the distance to be x. Here also I choose a distance x. Okay. Now what happens? The wavelets from A can undergo bending. These light rays can undergo bending. After bending, the wavelets can reach at point P1. This undergo bending at an angle theta. Similarly, from here also light rays can travel like this. Okay. So this angle also will be theta. And from point C also we can represent. These are traveling to the point P1. So wavelets from A and B are reaching at the point P1 after diffraction. After bending through an angle, they reach here at the point P1 from A, B, and from each and every point on this wavefront. There are wavelets after diffracting through an angle, they are reaching at the point P1. What's the angle of diffraction? Theta is the angle of diffraction. Now definitely we can say that there's a path difference. So between the wavelets from A and B, there's a path difference. How can you find a path difference? I can draw a perpendicular line to the perpendicular line here. This is N. So BN. So I'll draw the figure once again here. This is the width of the slit. This is the point A. This is B. And this is a perpendicular line. Okay, this angle is 90 degree BN. What will be the BN? BN will be definitely equal to path difference between the wavelets traveling from A and B to the point P1. We need to find the path difference. Since this angle is theta, this angle also will be theta. By geometry we can show that this angle will be theta. What is the width of the slit AB? This width will be equal to, I can give a symbol small a. So width is small a. So what is sine theta in the figure? Sine theta is equal to opposite side, that is Bn, by hypotenuse small a. So what is Bn? Bn is equal to A sine theta. Okay, If theta is small, what we can say? Bn, path difference Bn is equal to A theta. This is our fundamental equation. The path difference between wavelets starting from A and B to the point P1 will be equal to A theta. You got the path difference. Okay. Now similarly, similar diagram we can draw at point P2 also. After diffraction, the wavelets, the same angle of diffraction, the wavelets will start to travel to the point P2. Here also wavelets will start to travel to the point P2. From center also we can draw wavelets. What is angle of diffraction? Here also angle will be theta. So these 2 points we have considered on either side of the center. Now let us choose that this path difference Bn, let it be lambda. So here path difference was 0. At the point P1, next path difference we can take it as a lambda. So I choose the path difference Bn is equal to lambda. That is A theta is equal to lambda. Now what happens? This means that path difference between wavelets from A and B is lambda. See, if you take the middle point between A and B, then what will be the path difference between A and C? Since this path difference is between A and B, if it is lambda, path difference between wavelets from A and C and B will be half of that, it will be lambda by 2. So I can write path difference between wavelets from A and B, if it is lambda, then that between A and C will be lambda by 2. That between B and C, that also will be lambda by 2. Okay. Now what happens? We can divide this, we can draw this region once again separately, slightly bigger in size. So I just draw this slit portion separately in bigger size. This is a slit of width smaller. This is a point C, this point is A, this point is B. Okay. So path difference between wavelets from A and B, I choose this path difference from A to B is lambda. Then between A and C, wavelets from between A and C, path difference is lambda by 2. Here also lambda by 2. Okay. Now I can find many pairs from here to here, many pairs of sources of secondary wavelets. For example, I consider one source here, x1, source of secondary wavelet. Another source I choose here, x2. What should be the path difference between the wavelets from x1 and x2? Because if this is lambda by 2, this is also corresponding to lambda by 2. Okay. So between x1 and x2, path difference will be lambda by 2. I choose another point, y1. Okay, below here I choose another point, y2. Now this also can be lambda by 2. Means if you take the length from A to C, if the length from A to C is 1 millimeter, the length from x1 to x2 also can be 1 millimeter. From y1 to y2 can be 1 millimeter. So sources from x1 and x2 will produce wavelets to the point P1. Then what will be the path difference between the wavelets from x1 and x2? It will be lambda by 2. From y1 and y2 will be lambda by 2. Another point we can choose, z1. Then here z2. From z1 and z2 it will be lambda by 2. What happens? When wavelets, pairs of waves from wavelets from x1 and x2, they differ at a path difference of lambda by 2. y1 to y2, lambda by 2. z1 to z2, lambda by 2. So, if path difference between wavelets or the wavelets reaching at a point P1 is lambda by 2, we know that it will create a destructive interference. If it is lambda or path difference 0, it will be constructive interference. But if path difference between wavelets of x1 and x2, if it is lambda by 2, y1 and y2, lambda by 2, z1 z2, lambda by 2, what type of interference we can expect there? There will be destructive interference. So what will be the point P1? The point P1 will be a dark point. So I can write here, this point will be a dark point. And this point will be a bright point. So this will be a dark point and this will be bright point. Okay, so we can say this will be a dark point and this will be bright point. Similarly, at this point, we can see same angle of diffraction. This also will be a dark point. So P2 also will be a dark point. This is a dark point. So this is the first dark point on either side. This is the central bright band. So up to this region, here we have maximum intensity, maximum brightness. The brightness goes on decreasing, and here we have dark. Here also maximum goes on decreasing. Here we have. So at this point corresponds to maximum brightness region. The brightness goes on decreasing. Okay, this is called a central maximum. So the width, what is the width of the central maximum? X plus x, 2x. So the region from P1 to P2, from P1 to P2 on the screen, region from P1 to P2 on the screen is known as what? We can call it central maximum. So on the screen we will get a central maximum. Now we can see that in the figure that this is the slit. Slit is having a width only this much. But on the screen we have a bright portion. The width is more than this. We can see the width is almost 2 times or 3 times depending on the distance. So the width is large. Okay. So on these 2 points P1 and P2, we have which band here, which portion produced the dark portion. Here it is up to this point bright portion from P1 to P2. Then at point P1 and P2 we have dark region. Intensity is maximum at the center. Then the intensity goes on decreasing like this. Okay, so what's the condition we have got? We have got A theta is equal to lambda. When path difference between wavelets from A and B, if it is lambda, what we have got? We have got current destructive interference. Why? Because we can divide the region between A and B. We have a large number of points. Each point can be considered as source of secondary wavelets. If this width is lambda, means path difference between wavelets from A and B is lambda. Between A and C, we can say it is lambda by 2. Between C and D, lambda by 2. Between x1 and x2, we can consider lambda by 2. y1 by 2, lambda by 2. z1, z2, lambda. We can find many such pairs. From each such pairs, the wavelets will meet at the point P1 and interfere destructively, and this point we will have a dark point. Okay. Now we need to find the width of central maximum. Okay, what is the width? X plus x, 2x. So width, we need to find width of central maximum. I choose this value W. W we need to find out. What is W? W is equal to x. Now the distance between the slit and the single slit and the screen we can choose to be capital T. Now if you consider the triangle here, okay, we need to this angle is theta. So in this triangle B, I can say B, this we can consider. This angle also will be theta. So C P1O. In triangle, right angle triangle, C center P1O. C P1O. When you consider this right angle triangle, C P1O. What is tan theta? Tan theta is equal to opposite side x, adjacent side capital D. So x by D. Of theta is small, theta is equal to x by D. Okay. Also we have got theta is equal to lambda by A. Here we have theta is equal to lambda by A. We have got 2 equations for theta. Equation number 1, equation number 2. Equating these two, what we have, x by D is equal to lambda by A. What is x? X equal to D lambda by A. Or what is 2x? 2x equal to width of central maximum, that's equal to 2D lambda by A. This is the width of central maximum. So we have got a width of central maximum. So due to diffraction, what happened? The slit is small in size, but the image, when the light rays fall on the screen, then we are getting a bright portion not up to this width. The width is increased. This width is called the width of central maximum. On either side of central maximum, we are getting dark points. These two are the dark points P1 and P2. Okay. Now it is observed that we are getting a diffraction pattern due to the single slit experiment. Then if this is these two are dark points, if we consider other 2 points, we can say this is P3 and we can say this is P4. At these points, we will get again bright region. But brightness will be less than this. Again, we will get dark region. So, we will get alternate dark and bright bands on the screen. That pattern is called a diffraction pattern. The formation of diffraction pattern that we will see in the next class. Okay, thank you.